Hello everyone, I am Jignisa. I am pursuing my MTech from NIT Delhi. So today I will be present probabilistic roadmap. This is the table of content. What is probabilistic roadmap? Learning phase, then query phase, algorithm, example, application, drawback, references. So what is probabilistic roadmap? The probabilistic roadmap is a planning algorithm used in robotics and computational geometry to generate a path between two points in a high-dimensional space. It works by constructing a graph of configuration space which is the set of all possible configuration of a robot, and then using robotic sampling to generate a set of points in that state. Uh, and this is the one type of approximation roadmap. PRM is constructed from a set of configurations sampled from C space, and it can be called probabilistic roadmap because the number of samples tends to infinite. Likelihood that the graph is the roadmap goes to 100%. Learning phase. In the learning phase, the probabilistic roadmap is constructed by repeatedly generating random free configurations of robot and connecting these configurations using some simple but very fast motion planner. We call this local planner. The roadmap thus formed in a free configuration space of robot is stored as undirected graph R. The configurations are the nodes of R, and the path computed by the local planner are the edges of R. The learning phase is concluded by some post-processing of the R to improving its connectivity. It constructs a network of paths in free C space. Previous roadmap methods include the visibility graph, Venn diagram, and silhouette method. All these three methods computed in a single sort of roadmap that completely presents connectivity of free C space. The visibility graph and Venn diagram methods are limited to low-dimensional C spaces. The learning phase consists of two successive steps: construction and expansion step. First, we will see construction step. In construction step, initially graph R and A is empty. Then repeatedly the random free configuration is generated and added to node, and for every such new node C, we select a number of nodes from current N and try to connect C each of them using a local planner. Uh, so uh, this is the uh, this is the figure in which it can source the nodes and connectivity of its graph. The selection of nodes to which we try to connect C is done as follows. First, n of candidates neighbor is chosen from n. This set is made from nodes within certain distance of C for some metric D. Then we pick node from N in order to increase the distance from C. We try to connect C each of the state selected node if it is not already graph connected to state. Hence, no cycle can be created and the resulting graph is forest. Collection of trees, since a query would never succeed thanks to an edge that is a part of cycle, it is indeed sensible not to consume time and space computing strong such as edge. The expansion step. If the number of nodes generated during the construction step is large enough, the set n gives the fairly uniform covering of free space. In easy sense, R is then well connected but is more constrained. Once where free space is actually connected, R often consists of few large components and several small ones. It therefore does not effectively capture the connectivity of CF. This is the expansion step where each node is connected, um, its neighbor node by connected by edge. The idea underlying the expansion step is to select a number of nodes from N which is likely to lie in such a region and to expand them. By expanding configuration C, we mean selecting a new free configuration in neighborhood of C, adding this configuration to N and trying to connect its neighbor of N. This is the formula for ratio of for calculating the ratio of failure ratio, where NC is the total number of time of local planner try to connect to another node, and f of c is the number of times failed. So the query phase. During the query phase, paths are to be found between arbitrary input start and goal configuration using the roadmap in the learning phase. Assume for a moment a free space is connected and the roadmap consists of single connected component R. Given start configuration S and goal G, we try to connect S to G using the feasible paths. If it fails, then query fails. Uh, this is the query phase uh, where start and goal are connected using the um, feasible path. So, the To construct a PRM, we can use this algorithm. N is the number of nodes in the roadmap and K is the number of closest neighbor for node. Um, each node. This phase configuration can be generated by uniformly randomly sampling the C space and only keeping the sample if it is the collision free. But the non-uniform sampling strategy can also be used to increase the likelihood that the PRM is able to represent narrow passageway in C space. The and free space configuration generated in the first phase of the algorithm uh, nodes of a graph. The second phase of algorithm tries to connect nodes with edges. For each node, we find the set of k nearest neighbor. Then for each neighbor nodes, we try to find the path from original node to neighbor. To do this, we use a very simple and fast local path planner which does not attempt to mm, avoid the obstacles. For example, the planner could just choose a straight line between the original node and the neighbor. We, uh, we can then check whether a path is collision free, and if so, we add edge between two nodes. Then examples. The examples of task meeting these conditions include maintenance of cooling pipes in nuclear plants, point-to-point welding in car assembly, and cleaning of airplane fuselages. Uh, in such tasks, many degree of freedoms are needed to achieve successive desired configurations of an factor while avoiding collisions of rest of arms with complicated workspace. Exploiting programming of such robots in tedious and time-consuming, an efficient and reliable planner would be considerably reduce the programming burden. And this is the application of PRM self-driving car uses the self-driving car uses the PRM to decide uh, where they want to go. Then drawback of PRM. Assume that the gap between two obstacles is very narrow. Recall that our system generates nodes randomly. Due to this probabilistic road probability of generating nodes between those gaps is very small. The system might generate node in the region if we increase the number of iterations. So this is the example where PRM may be drawback. It creates a node where in such a small spaces. And this is the references where I can take this content. Thank you.